Tonight is June the 18th, 2021. I've got an interesting subject tonight that somehow caught my attention, and I want to show you something. I'm not going to tell you how to do anything. I just want to show you something and think about it. It's about standby switches in guitar amplifiers. Now, I don't work on guitar amplifiers anymore. I took them in for a few years, but I got overwhelmed with them. It's just too much work to do. I didn't have time for my own hobbies. But anyway, what I've built here is as goofy as it looks. Is a very simple power supply with a load out here. This resistor here. This is your amplifier, and this is the power supply, of course. Power transformer. It's got a choke in it. It's got a capacitor on the input of the choke. It's got a capacitor on the output of the choke. These little resistors right here don't do anything. I was using them earlier. They're just connection points. I know that looks pretty goofy, but that's what it is. Very simple little full wave center tap power supply. And what we're going to do is we're going to make some real measurements. We're not going to do what we think, feel, and believe. And we're going to get past some of this nonsense that you hear on the internet about cathode poisoning and interface resistance, and the worst one is it says that guitarists don't even know how to use the standby switch. Well, that's an insult. Look, let me show you what it's doing, and then you'll see where I'm going with this. Okay, this is a fancy little Tektronix current probe. We're going to be measuring the current coming out of the power supply. I've got it drawn in a couple of different places. We're going to be measuring it. Right now we're measuring it right there, coming straight out of what would be your 5U4 whatever. I got solid state diodes in there, of course. And this is where I would put it, with a resistor across it, a trickle charge resistor. I'll explain this in a minute. Or I would put it right there in the center tap. One of the two places, and I would put that trickle charge resistor on it in either place. And I'll show you why in just a minute. Let's look at what's coming out of that point right there. Let's scope in here on the scope and get it to turn back on. See, that's what's coming, that's the current that's flowing through that wire. Right here in the middle is zero. So we've got a positive pulse, we've got nothing flowing right there. There's no current flowing right there. And then we got a negative pulse. We got a positive pulse and negative pulse. That's reality. Now, what we want for our relays and our switches is relays and switches are rated different for AC than they are for DC. When you open up a switch, it only opens up 1 or 2 millimeters, those contacts. And when that happens, let's see, I think, yeah, here's a relay right here. Look at this relay. Hope this thing focuses. Not just focuses on the back part. Let me see if I can make this thing. Oh, come on. Let me turn this away a little bit so maybe it'll focus there. Yeah, right there. Okay, see those contacts? See, when it's on, these two contacts would be made. Now, if it's a DC relay, when you start opening them up, you get an arc right there. You get a little blue arc. You get a little spark when you close it. Now, if these contacts don't come far enough apart, then the arc is going to be sustained through there because it's got the air ionized. Now, these come apart far enough that they would probably extinguish the arc. But that's the problem. If this thing continues to arc, well, it's not, in 10 minutes it's going to be burnt up or less. So you got a problem. You got a completely different kind of a problem when you put a contact switch, a switch or a relay in a DC circuit, because you're never turning the current off. The current's flowing all the time, and then all of a sudden you open the switch and the current doesn't want to quit flowing. So it makes that arc, and if they don't come far enough apart, it never quits arcing. Well, when we're looking at this right here, it's going to quit arcing because the current goes to absolute zero. Right there. It does the same thing when I put it on the center tap. Okay, look, I'm going to move it over here. The green wire is the center tap. I'll put it on the center tap, or around it. We got the same thing except the opposite polarity. So we can put the switch at either one of those places and the current is going to quit flowing every cycle. Even probably every half cycle. Whatever. I think you see my point. If we put it over on the output, if I move the probe over to the output, well, you're not going to see anything because it's just pure DC. You don't see anything with an AC current probe clamped around a line carrying pure DC. Okay? So, what you want to do is you want to put your standby switch where the current stops flowing during each cycle. And that's right here and right there. Now, if you don't put this trickle charge resistor across it, what's going to happen when you close this contact is it's going to want to charge this big capacitor right here, and that's not going to make that's going to be really hard on your rectifier. It's probably not going to last very long if you turn it on and off a lot. So you put it right there, and you put a charging resistor across it, trickle charge resistor. I would use something like 100K, maybe 50K at 5 or 10 watts. Make it big. Same thing right here. This is probably a better place to put it. I don't think either place is better than the other, quite honestly. I think some of the old ones put them right there. And I think a standby switch is a good idea. I use standby switches on my transmitters. Matter of fact, I turn the whole thing on and off. Right out here, this is a relay in mine. I power the whole thing up and down every time I transmit and stop transmitting, because I got 4,000 volts out here. And if I bias the tube off, which some ham radio operators do, there's nothing wrong with that, then my 4,000 volts is going to soar up to over 5,000. And I'm just not going to, I can't walk away from a transmitter and leave it sizzling there with 5 kilovolts on it all the time. That's death on contact if something gets in contact with it. I mean, I've got it encased and nobody's going to be able to stick their finger in it easily. But still, it just makes me nervous. You know, high voltage got that zzz, sizzle to it. That's got nothing to do with this project right here. But what I just showed you, where the current stops flowing during each cycle, is right here and right there, not out here. So you're going to have arcing contacts out, arcing issues if you put it out here. And you won't have the same arcing issues if you put it there. You could also, to help extinguish the spark across it when these contacts open, you could put a little capacitor across it too, something like a, I think the usual value is something like a 0.1. It's got to be rated at quite a high voltage, because there's going to be a big spike there. Maybe something like a 0.1 at 1600 volts, some high voltage capacitor. And like I say, that resistor right there, I would make it somewhere between 50 and 100K, 50K and 100K at least 5 watts. So, this is not about what we think, feel, or believe. This is about what we can measure. So I hope this makes sense. I'm not trying to encourage anybody to put a standby switch in or not. I'm just saying if you do, it will make a difference where you put it. And I certainly see nothing wrong with it. I would have one in mine. You know, what you're doing is you're turning off the high voltage to the output tubes and letting them cool down. It's not going to hurt anything. It's not going to shorten their life. It's not going to poison them. I hope this was worth something, and you enjoy watching some of my crazy videos here, in my opinion. I got plenty of other videos coming up too. Thanks for watching. Y'all stay safe.